If I actually give a matrix like this kind of matrix, 3 by 3 matrix, we can find the iteration matrix for Gauss-Jacobi, Gauss-Seidel. Find the lambdas. You see, when lambda max is better, whether lambda max will be less here or more here. If it is less, of course, the speed is much faster. Correct? So that is the way we can think about the problem and we can verify the problem. I'll give you one example before extending further. X minus y plus z equal to 7. 4x minus 8y plus z equals to minus 21. Minus 2x plus y plus 5z equals to 0. This problem you keep in your mind. I'll come back. Okay? I'll come back. Think about how to solve by Gauss-Jacobi or Gauss-Seidel. Okay? Now, I'll be teaching you some more techniques. I will of course referring to this problem. That's why this problem is important. After Gauss-Jacobi, Gauss-Seidel has been done, people try to improve the speed of those techniques, iterative method, and some method has been devised called over relaxation method. It's called as Jacobi over relaxation or Seidel over relaxation. That means people try to do research on this algorithm, how to make the algorithm efficient, more efficient. So this is called as Jacobi over relaxation, and another is called as Seidel over relaxation. Okay. So first I will talk about Jacobi over relaxation scheme. Simple. We have xi k plus 1. We have what? 1 by ai. First we will write the Jacobi method. It's better. bi minus summation j equals to 1 to I minus 1 aij xjk minus j equals to I plus 1 to n aij xj. That was a Gauss-Jacobi method. We have to improve the technique. While improving, what the next researcher did, they said kxk plus 1 and xk. These are two next guesses. If we take some kind of weighted mean, that means if I put w plus 1 minus w, some kind of weighted mean, will it be better? So with that, what they did, they put here w and they put here 1 minus w xi. So they wanted to have weighted average or weighted mean. W could be any number. How to fix up the W? I am going to discuss now. So this is the modified Gauss-Jacobi method, and we call J over relaxation if W is more than 1. If W is greater than 1, we call over relaxation. If less than 1, under relaxation. Over relaxation, under relaxation. Okay. What is my iteration matrix for this? Whatever you do, final step is you have to find out iteration matrix. An iteration matrix, maximum value of maximum eigenvalue, you have to find out, and then only you can decide whether the method is efficient or not. My question is, what is your M matrix here? From here, one can write xk plus 1, mxk plus c. What is m? What is c? Find out, give me the answer. Find out and give me the answer. What is M matrix and what is C vector? What is M matrix and what is C vector? Remember that you have to arrange this such a way it will be xk plus 1 equals to mxk plus c. Just now we have done this exercise. What is M matrix? I mean, M matrix Nikita, M matrix this time possible or not? The way same way what we have done for the Gauss Seidel. I into
1 minus f minus n minus q into d.
Okay, first term is d inverse minus or plus minus d inverse. Put w first because scalar quantity no. Then into L plus q plus 1 minus w. Excellent. Done. Okay, this is the M matrix. C vector. W into. That's it. How to find W? I didn't tell you. We cannot just like the fix up some number for W. How to find W? How to find this W? What is your objective? Tell me, then I will tell you. You got this M matrix fellow. Rho M must be less than equals to 1. That means lambda max has to be less than equals to 1. That means what? This lambda max is a function of rho W. Right? Because if you look at D has numbers. How to construct D? That from here 4, 8, 5. 4 minus 8, 5. L matrix will be 0, 0, 0, 4, 0, 0, minus 2, 1, 0. U matrix is 0, 0, 1, 0, 0, 1. Sorry. So upper is this one. Minus 1, 1, right? This will be next will be 0. This will be 0, all 0. So the D matrix, L matrix, U matrix are unknown. But now this omega fellow is also there. W fellow. So W will be multiplied with D inverse. What is D inverse? It will be 1 by 4 minus 1 by 8, 1 by 5. You put W, you will get W D inverse. If you multiply, your M matrix will be having W. Got the point, right? Then, if you find lambda max, it has got W term. Other numbers, so W will be the value. Okay? So then, this lambda max will be a polynomial of W. Polynomial of W. 2x plus 1. Where fx will get minimum or maximum. dfx by dx equals to 0 has a chance to have maximum or minimum. d2f by dx square greater than 0 is minimum. Same thing here. You have the polynomial, you take derivative with respect to w equal to 0 equal, you get the condition. That same thing, same value of w, you put in the double derivative, you see whether you are getting positive or negative. If you have positive value, you get minimum, negative value maximum. That is the way one can find w. This problem is coming in the exam. But I will give you only 2 by 2 matrix, remember that. Not 3 by 3. 1 by 1 I cannot give you. That is only US guys can have 1 by 1. They can have 2 by 2, but this time I am thinking I will be behaving like US because we all follow US. Even our Prime Minister is also going to US. So we should also follow US. Okay, so 2 by 2 matrix is fine, right? So we will be giving 2 by 2 matrix, not 3 by 3 for this problem. For this particular problem, I am asking 2 by 2 only, not 3 by 3. Understood how to find W? At least 5 marks you can get in the end semester. 5 marks will be there. Clear? So that is the way one can actually find W. Okay. Now quickly tell me SOR, Gauss-Seidel integration matrix. What will be the situation? Xi k plus 1 will be W aii bi minus j equals to 1 to I minus 1 aij xj k plus 1 minus j equals to aij xjk. Am I correct? Let me check. Sometimes I forget things. Yes, I am correct. This is the plus 1 minus w xi. This is Gauss-Seidel relaxation method. Same thing will happen. You find out a matrix, rho n, spectral radius less than equals to 1, find w. If w is greater than 1, it is over relaxation. If w is less than 1, which is under relaxation. Right? Now there are some properties. You please write down the properties. Write down the properties. If matrix A is strictly diagonally dominant, if matrix A is strictly diagonally dominant, then the Jacobi iteration scheme converges for any starting vector. If a matrix A is strictly diagonally dominant, then the Jacobi iteration scheme converges for any initial starting vector. If you look at this system, this is diagonally dominant, 4 minus 8, 5. What you can see that along this is maximum, along this is maximum, along this is maximum. Now what I can do, 4x minus y plus 2 equals z equals to 7. I can write minus 2x plus y plus 5z equals to 15. 4x minus 8y plus z equals to 20. If you look at, it is not diagonal dominant matrix. See, if I give you this kind of system, and if you blindly apply your Gauss-Jacobi, this will not work. If I am naughty, I will give this kind of problem. I say apply Gauss-Jacobi. You are completely gone. You will give some initial case, you don't work. Because the rule I have given, the rule is the diagonal dominant matrix, and how it can be proved? How it can be proved from the formula? If it is diagonally dominant only, if it is diagonally dominant, they don't need to work, otherwise it won't work for any starting vector. How to prove it? Xk plus 1 Gauss-Jacobi minus D inverse L plus U xk. I am taking Gauss Jacobian. You have seen the M matrix, right? What is L plus U? We can write this as A minus B what we can write then? B inverse B minus A xk just put the minus sign inside, nothing else. What we can write? B inverse B equals to I matrix minus so now we can see that your iteration matrix is coming to this way. How can it look like iteration matrix? 1 0 0 0 1 0 0 0 1 minus B inverse 1 by A 1 1 A 2 what will you get? If you multiply, what will you get? One, 1 0, then 0, 1 0, then 0 0. Sure. What is actually happening in iteration matrix? 0 what? Sure. Are you sure? Huh? First term is what? 1. Second term? That's what you guys are becoming very lazy. All 0 means you just put 0. That's what I'm thinking. A matrix 0, then what kind of algorithm it is? Then you don't have to do all the exercise. Because everything is 0 only. Whether it work finding initial case, yes. Then next is next is 0. It is 0. 0. Okay, 0. Then 1. Then A32 by A22. 0. Then this is also 0. I don't know why I don't have the answer. Is it correct what I am getting? Is it correct? Yes or no? Yeah. Tell me the answer correctly. Nikita is not saying correct answer, it says. See, it is a matter of multiplication of the things. If you don't know how to multiply the matrix, I don't know what room I am reaching. This is multiplication. What actually happens? It is 1, correct. Now this into this, what actually happens? A1 to by A1 0. Then this into this, it is coming A1 to 0. Next is this into this, it is 0. This into this, it is coming as 1. This into this, it is coming as A. What is that? A21 by? First one is what? 1 person, please. 821 by 822. Then next one is 1 is correct. Then next one is
832 by 822.
832 by
823 by
I don't know what is actually happening. Simple, then you don't expect me to, if I have to fight out with the matrix multiplication, then I don't know how much advanced I am teaching here. What is that, madam? 823 by 822. Then next 831 by 832. Then 832 by 833. This 832 or 833. Next is 1. 1. Is that correct? Isn't it? Okay. Now, what actually happens? If you subtract, it will be 0. If you subtract, what will happen? Diagonal terms will go 0, right? Diagonal terms will go 0. Okay? Diagonal terms will go 0. So now, from here, it is possible to prove that you have to prove that this row of m should be less than 1, or lambda max should be less than equals, should be less if 1 by ai summation j equals to 1 to n, j not equals to I, mod aij less than 1 for all I. It means what? It means if you add 4 and minus 1 and 1 mod 1 plus 1 equal to 2, which is less than equals to 4, right? Second one is 4 plus 1. So this I am referring to not I, right? Correct? Second one is 4 and 1 5, which is less than equals to minus n, right? Mod of minus n. So this has to come from here. That we have to prove. This has to come from here. Okay? If this is proved, then only it is working. That is also one of the possible questions in the exam. So what you have to find out, you got the 0 0 0 this entire matrix. Find out the lambda and see that whether you are getting this kind of thing. Maybe one day Vasudha can actually give me the proof whether you are able to get it. If it works, that means the Gauss-Jacobi Gauss-Seidel will work for the diagonally dominant matrix. And then the last question actually I am trying to give you, if A is a strictly diagonally dominant matrix, then Gauss-Seidel iteration scheme, same thing actually I am giving. Gauss-Seidel iteration scheme will convert for any initial guess. Gauss-Seidel scheme will convert for any initial guess. Okay, another question I am actually having. If A is symmetric and positive definite, then Gauss-Seidel and Gauss-Jacobi methods converge for any choice of initial guess. If A is symmetric and positive definite, then the Gauss-Seidel and Gauss-Jacobi methods will converge for any choice of initial guess. What is symmetric positive definite matrix? Symmetric matrix is Aij equals to Aj. What is positive definiteness? How to prove it? Did I prove it? Who proved it? Which class? Thermodynamics, yes. What part of thermodynamics you proved? Thermodynamics? Stability, excellent. Thermodynamics stability. Good. How to prove it? For any matrix, eigenvector is x, lambda x. But omit is saying all lambda is positive is the property of positive definiteness. For a matrix to be positive definite, the rule is that for any vector, inner product has to be greater than equal to equal to means positive semi-definite. If equal to sign is not there, positive definite. This any vector could be eigenvector also. Any vector means eigenvector also, right? That means I can replace this as, right? Or I can replace this as, this is the length of the vector. Cannot be 0. Lambda is greater than 0. If it is not eigenvector, then how to prove it? If it is not eigenvector. This kind of process should be coming in our exam. This is not thermodynamics, this is math. So all those things have to be proved. Eigenvectors. That means any vector can be expressed as linear combination of I equals to 1 to n. right? So when we write AX, that means what? We can write A summation I alpha I y bar, comma summation alpha I y bar I equals to 1 to. What should I write then? Summation alpha I lambda uy bar summation I equals to 1 to n alpha uy bar. Next step. There's no matrix here, no matrix anymore. Then this has to be equal to 0. Remember that. What will actually happen? For symmetric matrix, what actually happens? All eigenvectors are orthogonal, right? I am talking about now symmetric positive definite matrix. All eigenvectors are orthogonal. That means inner product if you take, so it is like say two vectors are there, alpha 1 q1, sorry, lambda 1 q1, lambda 2 q2 plus lambda 3 q2. Inner product with alpha 1 q1 plus alpha 2 q2 plus alpha 3 q2. How to take inner product? We have the property, right? B plus W, U plus B, W plus B plus W, all properties are there. So apply the property. And in that case, you can see that U1 inner product U1 is 1, but U1 inner product U2 is 0. Because symmetric matrix, I am saying. Same thing. Then you can see that even for this case, it is possible to say that if all lambdas are positive, then only this is satisfied. Because our rule is that for any vector x, positive symmetric positive definite matrix x equal to greater than equal to 0, then all lambdas are to be 0. So this has to be applied to prove that Gauss and Jacobi and Gauss-Seidel method would be working better than Gauss-Jacobi. Okay. So with that, actually, I will end the algebraic system. Now we will be talking about the differential system. I will take only 10-15 minutes. Differential equation. Okay. We have to solve. We saw ODEs. We saw PDEs. We have seen ordinary differential equation, partial differential equations. Okay. Ordinary differential equations. So d2y dx square plus 3 dy dx plus 2y equals to 0. This kind of system. It is possible to have analytical solution, but sometimes we may have this type of system, or 2y to the power, this kind of system. It is complex. We cannot have analytical solution. And the thing is that we need to do by numerical. What numerical will do? Express the derivative. The algebraic form. And what actually happens? This will lead to set of algebraic equations. This will lead to set of algebraic equations. This derivative. This will not be any more derivative. This will not be any more derivative. We'll convert the derivatives, wherever derivatives appear, in terms of algebraic system. That means derivatives can be expressed in terms of ratio. Okay, let's look at how to do that. We'll actually see calculus. definition of derivative from calculus. First level calculus. When you learn calculus, the first thing we learn, right? After the continuity and all those things, we learn this. And sometimes people write dx limit h tending to 0, f of xh minus f of x by h. This is your learned first lesson of calculus in plus 2 level. If I remove this one, what will happen? Will it be correct all the time? Sometimes it may be correct, sometimes it may not be correct. If we remove, this is an algebraic expression. If I put limit, there will be differential expression. If I put limit delta x tending to 0, you cannot say delta y by delta x. That's the introduction of calculus. If you put limit delta x tending to 0, then this entire quantity is not no more algebraic, rather it will be called as dy dx. But sometimes you can write dy dx by delta y by delta x. When you can write, there is no limit. If there is no limit, then you are very happy. Then you can say, sir, I can replace dy by dx by this. Okay, when can we do that? Slope is?
Yes, x is not
Like this slope, huh? You are saying something. That means that is the slope, there is no point to have differential equations. If I have y versus x, like this, then dy dx is what? 0, no. Why do you have differential equation in that case? That means, so any point if you look at, this is delta x, this is delta y. This same. Then in that case you can write dy equals delta y delta x. That means we can write this as delta y delta x if you see the slope is linear. But it is not the case. It is very unlikely. Even for this type of problem, you can get slope linear. Right? Then how to make sure some portion, same as slope is linear. So we can have some portion where slope is linear. Some portion where slope is linear, then we can always have. That means what? This is our domain, 0 to 1. This is the way my solution is. I don't know my solution, but somebody found the solution, I can tell you, okay, this is the solution. If you look at now some sectors, in this sector, the slope is linear. That means within this sector, I can say dy dx is delta y delta x. So within this sector, I may not have differential equation. I can replace the algebraic equation. So what will actually happen? I will have a small segment which I call as domain. They are all finite size. And this technique is known as finite difference method. This technique is known as, so we will be solving this differential equation along this small segment where the differential terms can be replaced by algebraic expression. Sometimes what actually happens, this may be computationally expensive. What may happen? You are getting the expression dy dx, which is not delta y by delta x, but quadratic variation. is possible to have expression which is a quadratic curve dy dx. So in that case, if you can capture the quadratic curve, you may not need so many points. That means higher order approximation less CPU time, more efficient, so now next we will be talking about how to have dy dx d2y by dx square algebraic expression with higher order approximation such that we will take less number of nodes. These are basically called as nodes. These are basically called as nodes. We will take less number of nodes and we can have efficient algorithm. For that purpose, to obtain the algebraic expression, the fundamental thing we will be writing as Taylor series. We will be working on the Taylor series. What is Taylor series? F of x plus h is equals to f of x plus h f prime x plus h square by 3 factorial f double prime x plus h cube by 3 factorial f triple prime x and so on. What it says is f of x plus h. That means any function which is slightly perturb with respect to x or slightly change the value with respect to x, it can be expressed in terms of x but with infinite terms, provided all infinite derivatives are available. Sometimes some of my friends will cut or truncate. You will say, I won't say do all those things. We are becoming very lazy and how we will do all those. Sometimes what actually happens, this may be correct also. If we truncate, truncate means to take scissors and cut it. Discard it, throw it to dustbin. All this stuff. You just say, no, my term is like this. If you do that, what actually happens? You can write f of x plus h minus f of x equals to h f prime x, and there is the order of error, the order of h square. So if you truncate, maximum is h square because remember that h is fraction. That means f is 0, 1. H square is say 0, 10 to the power minus 4. H cube will be 10 to the power minus 6, right? That means this is the leading order error. If you cut it out, this will give the maximum value of error. So always you should write this is the order of error. And then what actually happens? F of x plus h minus f of x by h f prime x plus order of error h. I am dividing all side by h. That means we can write this as f prime x is nothing but f of x plus h minus f of x by h with minus order of h, or sometimes we can say order of error is h. So we have derived a derivative formula df by dx in terms of algebraic expression from Taylor series, which is nothing but f of x plus h minus f of x by h. Order of error is h. Now the thing is that if h is equals to 0.1, we get order of error equals to 0.1. Okay? And what actually happens, you may be having more accurate. You can say that, okay, I want 0.1 error is lot of error. I want to reduce my error. That means if you have order of error h square, which is 0.01, or order of error h2, which is 0.0001, in that case that formula is better. Okay? So those kind of things can be also done from the Taylor series. So let's look at a more formal way how to get the derivatives for the nodes. So this is my domain 0 to 1. First node is second node, third node. This is my nth node and this is my ith node. This is I plus 1 equals, this is I minus 1. If I want to write dy dx at particular node, because so what is our objective? Objective is some differential equation we have d2y by dx square plus 3 dy dx plus 2y equals to 0. To solve, to obtain equation at each node. Alright, that means when you apply the finite difference method, you write these equations at I, 3 dy dx at I plus 2y at I equals to 0. Right? That means these guys require algebraic expression. These guys require algebraic expression. Could be higher order approximation, could be lower order. So we'll be discussing in the next class how to have the expression and then proceed further. Thanks for paying attention.